Today, we're going to demystify something that's, an absolutely essential skill if you're into electronics, simulating operational amplifiers or op-amps using PSpice. This is really the secret to designing circuits that actually work right out of the gate.
Oh man, we've all been there, right? You spend hours, maybe even a couple of days, soldering all your components, you triple-check every single connection, you power it up and crickets. Nothing. Or, even worse, you get that little dreaded puff of smoke. It's so frustrating and it's a huge waste of your time and your parts.
And this is where simulation just completely changes the game. I mean, instead of these slow, expensive physical builds, simulation is fast, it's pretty much free, and it gives you this incredible insight into how your circuit is going to behave before you ever even touch a soldering iron.
So, here's our game plan. We'll kick things off with why this all matters so much. Then, we'll meet the key players, the inverting and non-inverting amplifiers. From there, we'll dive right into PSpice to design, simulate, and analyze the results. And to wrap it all up, I'm going to share some super common pitfalls so you can steer clear of them.
Okay, so why simulate first? Well, it's because just like a giant skyscraper needs a blueprint, your electronics need a really solid plan. And simulation, that is your plan.
I mean, think about it. You would never, ever try to build a skyscraper without a blueprint, right? The same logic applies right here. Simulation lets you find and fix all those potentially fatal flaws on your computer, saving you a world of headaches on the actual workbench.
All right, now let's meet the stars of our show. We're going to be simulating two really fundamental op-amp configurations that are, honestly, the building blocks for countless analog circuits out there.
So we have the inverting amplifier and the non-inverting amplifier, and the names pretty much give it all away. The inverting amplifier takes your input signal and basically flips it upside down. That's a 180-degree phase shift. The non-inverting one, well, it boosts the signal while keeping it perfectly in phase with the input. For the inverting amplifier, the real beauty is just how simple it is. The gain, which is just how much the signal gets amplified, is just a simple ratio of two resistors. And see that little negative sign in the formula? That is key. That's the mathematical proof of that 180-degree flip we were just talking about.
Now, the non-inverting amplifier uses the exact same two resistors, but the formula is just a little different. It's 1 plus the ratio. This simple little change makes sure the gain is always positive, which means the output signal stays right in phase with the input.
Okay, enough theory. Let's get our hands dirty, right? It's time to actually jump into PSpice and turn all these diagrams and equations into a virtual circuit. Building our circuit in PSpice really just boils down to 3 simple steps. First, we're going to pick our op-amp model. Then we add the resistors that are going to set our gain. And finally, we set up our input signal so we can actually test the circuit. Easy enough.
For our little example here, we're going to use the classic 741 op-amp. Now for the inverting circuit, we'll use a 10K ohm feedback resistor and a 1K ohm input resistor. For the non-inverting one, it's going to be 10K and 2K. And our test signal, a simple 1 volt, 1 kilohertz sine wave.
With our circuit all designed, it is time for the magic. We are ready to run the simulation and really put our virtual creation to the test.
So we're going to focus on 2 main types of analysis. First is transient analysis. Think of this like a virtual oscilloscope. It shows us the output waveform over time so we can actually see our sine wave getting amplified. Then there's AC analysis, which is a little different. It sweeps through a whole range of frequencies to test the amplifier's performance limits.
Okay, this is it. The moment of truth. We've done the theory, we've built the virtual circuit, and now we get to see if the data actually matches up with our predictions. And check it out, the results are in. For our inverting amplifier, the theory predicted a gain of -10, and boom, the simulation confirms it. For the non-inverting, we expected a gain of 6, and it is a perfect match. This is that awesome aha moment where the simulation proves your design is solid.
But hey, gain isn't the whole story. We also need to check for stability to make sure the amplifier isn't going to just oscillate like crazy. And for this, we look at something called the phase margin. Think of it kind of like a safety buffer. A value over 45 degrees is a really good sign that our circuit is stable and it's not going to misbehave on us. You also really want to just visually inspect the output waveform. I mean, use your eyes. If the peaks of your sine wave look like they've been flattened, that's called clipping. It's a dead giveaway that your op-amp is hitting its power supply limits and just can't amplify the signal any further. This is another one of those critical insights you get from simulation.
And finally, let's go over some of the common traps that can really trip you up when you're just starting out. Think of these as pro tips to keep your simulations running nice and smooth.
First, seriously, double-check your resistor values. One little typo can throw everything off. Second, make sure you're using the right op-amp model for the job. Third, and oh my gosh, this gets everyone at first, don't forget to connect the power supply to your op-amp. It's not going to work without it. And finally, make sure your simulation settings actually match the signal you're trying to analyze.
And that's the real power of this whole process. PSpice is your electronic sandbox. It's a place where you can experiment, push the limits, and make mistakes without any real-world consequences. It's how you test your ideas safely and efficiently, and ultimately how you become a much, much better designer.
So, you've now seen how to turn a theory into a validated virtual circuit. You've simulated the foundation. So, the only question left is, what are you going to build next?